Okay, so for the final, anybody has questions? And by the way, final covers chapter 10. That's it. So, who has question? You guys hear me, by the way? Is there any other problems that you can send us for practice with answers? Actually, I think I do. Notes. Is it this one? Yeah, it's this one. Let me send you guys this right now. Save problems. But it doesn't have solution. I'm gonna email to you right now. New 20. Here we go. Okay, detached series problems. Okay, so you should receive it shortly. But in the meantime, does anybody ask a question? Okay, you should receive it. All right, so did you get it? Can do one from the quiz. Actually, the quiz questions. Yeah, I can do that. So the one from the quiz. 2n factorial. I think it was this one. I think it was x to the n over 2n factorial. N from 0 to infinity. Right? Is it the one? Opening that quiz. Quizzes. Quiz 11. Yes, that's the one. Okay. And it's asking for interval of convergence. Okay. Well, we set this up. So for any x in R, not for any, for x inside real number set, we set this up, take limit of it, and we set it less than, strictly less than 1 and approaching infinity. But bn plus 1 over b sub n is x to the n plus 1 to n plus 1, oops, 2n plus 2 factorial 2n factorial x to the n, which simplifies to absolute value of x divided by, if you 2n plus 2 factorial is 2n factorial times 2n plus 1 times 2n plus 2. So we get 1 over 2n plus 1, 2n plus 2. Okay? And when you take limit of this, it's absolute value of x, and then the limit of 1 over 2n plus 1, 2n plus 2. That's 0. So what does it mean? That means no matter what x is, this means for any x in R, series converges. So the interval of convergence is negative infinity to positive infinity, or the entire R set of real numbers. Okay. That was part B. I'm going to write this. Quiz 11, 1B. This is 1A. How did you get 2n plus 1, 2n plus 2? Well, the denominator is 2n factorial, right? Is 2n factorial. Now, instead of n, I'm plugging n plus 1 factorial. So this is 2n plus 2. When you distribute, factorial, which is the last number is 2n plus 2. The one before is 2n plus 1, and the one before that is 2n, and then rest of that, which is factorial. So when you divide this 2n factorial by this guy, the 2n factorial cancels. So if you go back here, between these two, 2n factorial cancels, and then those two terms are left. It's like dividing 6 factorial by 8 factorial. The simplification is 7 times 8. Mhm. 1a. 1a is this guy. And then 3 to the n. And then from 0 to infinity. First of all, of course, you can do this with the whole, again, b sub n plus 1 over b sub n ratio. But someone could argue it this way as well. If you write this whole thing as x minus 2 over 3 to the n, and from 0 to infinity, then this is a geometric series. Right? Where the ratio, in fact, if you span it, it's 1 plus x minus 2 over 3, to the first, plus the third term is x minus 2 over 3 squared plus so on. Now, when does this converge? So this geometric series converge for those x's for which this ratio is strictly less than 1. And then you solve for x. So absolute value of x minus 2 is less than 3. In fact, this is the radius of convergence. But the interval is, x minus 2 less than 3, bigger than negative 3, add 2 is 5 minus 1. Which makes sense, right? Center is 2. And then move 3 units by this side. 3, you get negative 1. 3, you get 5. But interval is negative 1, 5. Okay. But if you set up the limit, this would be the answer of the limit. Like if you simplify it, bn plus 1 over bn. The rest of it is there. Question now. 2a. 2a, we want to find the power series for this guy. Okay. And the power series for, the geometric 1 over 1 minus x is given. So this is what we do. We factor 5 and 3 out of the denominator. Doing that, we get 1 over 1 minus x over 3. Okay. And then we use that power series formula. So 1 over 1 minus x would be the powers of x to the n. Here, you have x over 3 to the n. And starting from 0 to infinity. So that's 5/3. In fact, that one is quack. But if you want, you can write it as x cubed over x to the n. 3 to the n. And from 0 to infinity. That's that one. Now, 2b. For 2b, we know 1 over 1 minus x is this guy. We know 1 over 1 plus x would be sum of negative x to the n for all of them 0 to infinity. integrate this. So from here to here, x goes to negative x. From here to here, integrate. Let me write it this way. If you integrate, you get natural log of 1 plus x equals first of all, this is negative 1 to the n, x to the n. So it would be negative 1 to the n, x to the n plus 1 over n plus 1, and from 0 to infinity. Okay, now we can write out the one that we asked. We asked to find the power series. Well, simply replace x with x squared. So that'll be negative 1 to the n, x squared raised to n plus 1 over n plus 1, 0 to infinity. Now, just simplify. So it's x raised to the 2n plus 2 over n plus 1, and from 0 to infinity. That would be it. Question on now? Notes? Serious problem? Okay, what else? Can we review telescoping series? Let me see if there's one in this example. Telescoping in general have this form. You can write them as bn minus bn plus 1. And from 0 to infinity, or 1 to infinity, it doesn't matter. Because if you consider the partial sum of this, limit of bn minus b sub n plus 1, and from 0, let's say, to capital N, and then capital N raised to infinity. If you write out the terms of that summation, the partial sum, so limit of n goes to infinity, plug n equals 0, so we get b0 minus b1, plus plug 1 now, we get b1 minus b2. You continue this, eventually you get b sub n minus b sub n plus 1. Now there are cancellations happening. b2, there's another b2. For bn, there's another bn before that. The negative sign cancels out. So what is left is b naught minus the last one. Okay. Now, this limit converges only if that one converges. So this converges if the limit of b sub n plus 1 and going to infinity is finite. It doesn't have to be 0. As long as it's finite, it's fine. Then it converges. Example, I'm not sure if I gave you this. Probably I gave it to you as a quiz question. Let me write it out. Example. The summation of tan inverse of n minus tan inverse of n plus 1. And from 1 to infinity. Okay. So same thing. Limit tan inverse of n minus tan inverse of n plus 1. And from 0, to capital N. Okay, it doesn't matter. Okay, going to infinity. This is limit. Okay, write out the sum, the partial sum. So it's tan inverse of 1 minus tan inverse of 2 plus tan inverse of 2 minus tan inverse of 3 plus tan inverse of, k minus 1 minus tan inverse of k plus tan inverse of k minus tan inverse of k plus 1. Close it. The limit as k approaches infinity. Now I can see a lot of cancellations. Those two with the next term, tan inverse of k minus tan inverse of k, and this one with the term before that. So everything in the middle cancels. We only left with the limit of tan inverse of 1 minus tan inverse of k plus 1. Now it converges, right? Because the value of that is pi halves. Okay. And what's the value of that one? This pi fourth. So pi fourth minus pi half is negative pi fourth. Finite element. That means this sum like the ultimate sum of this series is negative pi fourth. So if the limit of bn plus 1 goes to infinity, yes, correct, it diverges. Basically, the final decision depends on the limit of this term. Depends on the limit of this term. Okay. What else? You're welcome. This file that I just sent you, they're basically series problems from the Stewart's calculus book. There are 38 problems. It's going to be a good practice. And basically, you're only investigating if the series converge or diverge. That's it. Let me see if there's an interesting one that we can talk about. So 1, 2, 3, 4, 5, 6. Yeah, let's talk about this one. And from 1 to infinity. So question is, does this converge or diverge? Why? So what's the first thing you do? Enter test. So take limit of only this guy. As n goes to infinity. What is that limit? You ignore this n? If that n wasn't there, yeah, the limit would be 3 over 8. The limit of that is 3 over 8, you're right. Well, there's an n over there. is 0. Think about a limit of inside of 3/8. 3/8 is a number less than 1. If you raise a less than 1 number to infinity, or any number between -1 and 1, so the theorem was if absolute value of b is less than 1, then limit of b to the n and approaching infinity is 0. So that limit is 0. That means nth term test here is inconclusive. So we have to pick a test. We have a lot of tests, and they're all beautiful. They all work nicely. Right? Tremendous. Just good. We have integral. We have ratio. We have root. What else? We have comparison. Limit comparison. We have alternating. This is not alternating series. So what test is the most? Remember, there might be more than one test working here, but we want the most efficient, quickest. There you go. Root is the one. Because this is raised to n form, right? It's, it's a ratio or whatever, raised to the n power. So just go ahead and undo it by simply taking root test. Root test. Using root test, limit of the nth root of our nth term as n approaches infinity. The nth power and nth root cancel out, and now we have n plus 3n over 1 plus 8n as n approaches infinity. What's that limit now, Alex? That's 3 over 8. 3/8 is less than 1. So by root test criteria, since the limit is strictly less than 1, conclusion is that thus the original series 3n over 1 plus 8n to the n, and from, keep writing it, 0, 1 to infinity converges. Okay? Let me see. Number 7 is also 23. Tan inverse of 1 over n. Sure. Oh, tangent of 1 over n, sorry. Summation of tan 1 over n, and from 1 to infinity. So here a sub n is tan of 1 over n. Nth term test. The limit of tan 1 over n as n approaches infinity is, so tan 1 over n as n goes to infinity is 0. And what is tan of 0? That's 0. So this guy is inconclusive. Okay? So what do we do then? You have to do a test. Integral test. Let's see. When you say integral test, that means you have to ask this question. Are we able to integrate this function? Can we? The answer is we might be, but could be a very long way rather than maybe try another test, because someone could do, substitution here. 1 over x, let it be t, right? And then, so you have x is 1 over t, so dx is negative 1 over t squared dt. Okay, so it becomes dt. It becomes tan of t negative over t squared dt, and then it becomes 1 to 0, and you can switch it to 0 to 1, multiplied by negative. So it didn't even become easier. So integral test is not a good option. Integral test, not the best option. Not the best choice. So what else? So we're gonna ignore that. What other tests? Ratio is not going to work either. Root test and root of 10. Not sure what's going to happen. So there's one option left. Yes, comparison. Indeed, limit comparison is going to be the best here. We use limit comparison by using that guy. Now, let me explain how I got this idea. The nth term of the series we're dealing with is tan of 1 over n. 1 over n at infinity approaches to 0. So that means I'm dealing with equivalently tan of t when t approaches 0. Okay, let me explain again. I'm dealing with a tangent of the argument where the argument approaches 0. Okay. Now, so is there a limit? So this is what I'm thinking now. Is there a limit tan of, the argument where argument approaches 0, dividing by something else when the result is non-zero? The answer is yes. Now, I don't know if you remember from Calc 1. I think we also did it when we were talking about L'Hopital's. So what I have in mind is this limit. Oops. Is this limit. So what is that limit? Tan of t over t when t approaches 0. Because if you were familiar with this limit, you would have probably be able, to come up with this series and use it for limit comparison. The value of this limit is 1. You can simply use L'Hopital. Take the derivative of top, that's secant square of t. The derivative of the bottom is 1. Now, when t approaches 0, secant of 0 is 1. So the whole thing is 1. Okay. Anyway, this is where I got that idea. And why again? Because I'm doing tan of t dividing by its argument. Now, what's the argument of tan 1 over n? It's 1 over n. So that's why I consider this summation of 1 over n. All right, now let's continue. So we use this series, sum of 1 over n, limit comparison, and set and we find the following limit. Let me write down details. Our original series was tan of 1 over n. Okay. Now we're going to compare this with sum of 1 over n. Not direct comparison. We're going to do limit comparison. That was the criteria. We set up this ratio. We take limit of that. If this limit is non-zero, the conclusion is that both series behave the same. Let's see if it's non-zero. Well, it is non-zero. I mean, you can still use the L'Hopital for this. Take derivative with respect to n. Except on top, you have to do a chain rule, okay? How about this, Nisa? Negative 1 over n squared. Secant square of 1 over n. Chain rule. Negative 1 over n squared at the bottom. So as you can see, you have cancellations. The whole thing is secant square of 1 over n. As n approaches infinity, 1 over n is 0. Secant of 0 is 1. So it is indeed non-zero. Therefore, the two series behave the same. But that guy converges to diverge. Sum of 1 over n diverges. Because it's a p series with p equal 1, right? So that the summation of tan of 1 over n and from 1 to infinity diverges. Question on that one? No, there might be other ways to prove this or to show that this guy diverges. But you know, this is the simplest one. This is the one that gets us the answer fastest. But yeah, these are 38 good problems. Some of them, you've already seen them. Number 35, I'll give you on the quiz. Interestingly, they have it here. So, what else? Should I pick another one from this collection and do it? Let me see. Let's do number 37. So it's the summation of nth root of 2 minus 1, the whole thing raised to the n, and from 1 to infinity. Okay? So what do we have to do first? Let's figure out if the nth term test. Yeah. Remember, if the limit of an is not 0, you should be the happiest. Because right away you can say diverges. I don't have to do any tests. So let's figure out the limit of nth root of 2 minus 1 raised to the n and approaching infinity. Okay. What is it? If you plug infinity, the nth root of 2 is 1. Okay? Because think about it, you have 2 raised to the n, 1 over n approaches 0, 2 to 0 approaches 1. So 1 minus 1 is 0, that means you have 0 to infinity. Except this 0 is not exactly 0. So let's see. Oh, come on. 0 to infinity. So let's do exponential natural log. So exponential, so this limit is also same as exponential natural log of the limit of the same thing and approaching infinity. Let's switch natural log and limit, so it's exponential limit natural log nth root of 2 minus 1 to the n and approaching infinity. We can bring n right behind natural log, right? So that becomes the limit of exponential, sorry. So exponential limit n, and I'm going to bring n to the denominator, so it's going to write it as 1 over n. Let me do one at a time. Nth root of 2 minus 1 here and approaching infinity. So I'm going to write this as exp limit natural log of this guy, okay, and then 1 over n and approaching infinity. Let me one more time write it this way. Limit of natural log nth root of 2, I'm going to write it as 2 raised to the n minus 1 over 1 over n. Now we can go ahead and take hold on a second, there's a problem here. It's not infinity or 0 over 0. So I guess we could have just concluded that this limit is 0. Let's see. When I take limit of this natural log, that's 1. 1 minus 1 is 0. Natural log of 0 is negative infinity, whereas denominator is 0. So no, that's 0 right there. So we don't have to do this thing. You remember, the goal of doing this exponential limit is that on this limit, we should get a case of infinity or 0 over 0. If it's anything else, that means we're not allowed to do L'Hopital, okay? So what it means is that we don't even have to start here. 0 raised to infinity, so that's just 0. So let's erase that. Let me make it bigger. Okay, let's make it small again. So let's go back. But anyway, didn't work. The nth term inconclusive. So nth term inconclusive. Inconclusive. So we have to do a test. So question is, what test again? By looking at the form of the nth term, you can tell what the nth root. What test? Root. Well, the nth root of a sub n is the nth root of 2 minus 1 raised to the n. And simply nth root and nth power, they go away. So you have that guy. Now we take limit of this. So limit of nth root of a sub n is simply the limit of nth root of 2 minus 1 and approaching infinity. Now we know what that limit is. What's that limit? That's 0. It's less than 1. So by root test, it converges. So by root test, the summation of nth root of 2 minus 1 raised to the n and from 1 to infinity converges. Okay? So I suggest, working on these problems. Seems like a nice variety of series. Do you want me to find a similar one for power series and email it to you? Okay. All right, I'll do that. No, guess it should be all right. Email me if you have questions. I can get on this Webex meeting if you want to, But make sure you study and you have a good collection of questions instead of one question at a time. Even weekend would be fine. Your exam is on Wednesday, so you have time. Okay? If you don't have any other questions, this session is recorded, plus the PDF. I'll post it on e-learning. Let me stop.